out, title it tangents. Remember, we are not really connecting this at all to trigonometry. This is a totally separate application of the word, okay? Tangents, or tangent lines. So let's talk about what tangent looks like. Fonts were messing up. Okay. What does tangent look like and what does tangent not look like? So the one on the left, the green one, all of those are examples of tangent lines. A tangent line is a line that intersects the circle once and only once. Intersects the circle once. Not tangent would be the raspberry colored one, the one where all of those lines are either intersecting it twice, or 0 times. This is once, once, once. So that's how you identify a tangent line. It will, anyways. So the number of times it intersects will tell you whether it is a tangent or not. So here is the first theorem of the day. Oh no, my stuff is messing up because Smart Notebook updated. I'm sorry, guys. This figure should not look like that. Anyways, write this theorem down, please. Oh, you're just going to go away. Okay. If a line is tangent to a circle, then it is perpendicular to the radius at the point of tangency. It's not just perpendicular to any old chord, it's perpendicular to the radius. So it's really corny, but what I say over and over again, and it gets students to remember it, is that we say, when a radius meets a tangent line, you get a right angle. And you just say it over and over and over again, and then you'll never forget this theorem. When a radius meets a tangent line, you get a right angle. I even say it to myself when I'm solving problems. I'm like, ooh, is there a right angle there? And then I like say the chant, when a radius meets a tangent line, you get a right angle. And then I know whether to put a right angle marking or not. Okay. So, next theorem, let's see if we can come up with it by ourselves. What do you think is true about two segments that are tangent from an exterior point of a circle? So what is this exactly asking you to theorize about? So what it's saying is, I take a point. I put it anywhere I feel like, point A. We learned, after we did the basic terms worksheet, we learned that how many lines are segment to my circle that go through point A? 2 lines. There exists 2 lines. So I know from this point in the universe there are only 2 lines that are tangent to my circle. What I'm asking for is, what do you think is true about the length of those 2 tangent lines, the segments that we're talking about? So looking at all my examples, can you kind of tell? Maybe your hypothesis is that they're congruent. Do you think we could prove that? I bet we could prove that they're congruent. I'm going to draw this, and I'm going to draw this, I'm going to draw this. When a radius meets a tangent line, you get a right angle. When a radius meets a tangent line, you get a right angle. Let's try to prove those 2 triangles guilty of being congruent. Well, the radii are congruent, shared side are congruent. So we have hypotenuse, leg. Remember that really annoying song? Look, we just proved those 2 triangles congruent. So by CPCTC, I just love using proofs, this one is congruent to this one. So if 2 segments come from one point and they are both tangent, then they are the same length. That's what we are getting at. This is the theorem. You're not going to be asked to prove it, but I just wanted you to know where the theorem came from. 2 tangent segments from an exterior point of a circle are congruent. I call this the ice cream cone theorem because it looks like an ice cream cone. Here's your... That is the theorem. The theorem is that those 2 lines are congruent. So I call it the ice cream cone theorem. So ice cream cone theorem. 2 tangent segments coming from the same point are going to be the same length. Okay, so let's try to see if we can come up with the next theorem. The line through an external point in the center of the circle. So we're talking about line, this line segment OB in this picture. Blank the angle formed by the two tangent segments. The two tangent segments are AB and CB. What goes in the blank? Yes, very good. Bisects. So we could have already proven that because we've already proven those triangles congruent, and we use CPCTC to show that those two angles are congruent. So that's our next tangent theorem. That's our next tangent theorem. The line through an external point in the center of the circle bisects the angle formed by the two tangent segments. And we know that this comes from congruent triangles. It is cool, Johan. Thanks for saying so. Okay, the next thing is we're going to talk about common tangents. We're not going to talk about them too long because we're not going to be doing anything with them. We're not going to solve anything. I just want you to know what they are and what they look like. So we're not going to spend a lot of time on this. A common tangent is a line that is tangent to two coplanar circles. It just means they're in the same plane at the same time. So it's one line that's tangent to two circles at the same time. It would be called a common tangent because they have it in common. Those two circles have that tangent in common. Now, you can have a common external tangent or you can have a common internal tangent. How do you know the difference? How do you know if it's external or internal? Well, this will tell you the difference right here. If it's an internal one, it will intersect the segment joining the centers of the two circles. So, do those green tangent lines intersect that blue segment I just drew? Absolutely. Do the blue tangent lines intersect the segment I just drew? Nope, no intersection. So that's how you tell the difference whether they're common external or common internal. Chopsticks, they look like chopsticks to you? So just sketch a quick picture of what it looks like and just put external, and then a quick picture of what it looks like and just write internal. Don't spend a lot of time writing this. Let's see if we can try some examples of this. Before we try some examples, circles can also be tangent to each other. So anyways, you don't have to have a line to be tangent. To be tangent, we're just going to intersect each other one time. So this would be externally tangent circles because they're tangent on the outside, on the external part. And this would be internally tangent circles. Don't have to worry about this slide too much. Okay, let's try this one. Let's try putting to use our other slide that we saw. How many common external, internal tangents can be drawn? So like on A, how many, let's do all external first. On A, how many external tangents can I draw? Common external tangents on A. 2. Ganesh, thank you for being involved and being on task. I can draw 2 of them, so I'm going to put 2. What about on B? What about on B? Still 2 of them, so I'm going to put 2. What about for C? How many common external tangents? 0, 1. So is this an external or an internal tangent? Connect their centers. Does it cross that line? Nope. So it is external. What about D? What about D? Good. Once again, it's 2. And what about E? E. How many common external tangents for E? 0. 0 common external tangents. I cannot be tangent to both of those at the same time. You cannot. Okay, next one. Internal tangents. So for A, that we've already done the picture of that. For A, there's 2. What about for B? How many common internal tangents are there for B? Good. Just 1. What about C? Good. There are 0. 0 internal, common internal tangents. 0, 0. Is that okay? So this is kind of fun. We're not solving for anything. We're just making sure we know those definitions. Okay, here we go. Examples. BA is tangent to circle C at A. BA is 12. AC is 5. Let me show you the most common mistake so you never ever make it. Students will do this all the time. Don't be this student. And wrong, bad. Do not do that. So that's when you say the chant to yourself. When the radius meets the tangent line, you get a right angle. When the radius meets the tangent line, you get a right angle. Students will put the right angle in the wrong spot. So you never put the right angle at the center when the radius is meeting a tangent line. You put it where the intersection of the radius and the tangent line falls. Okay? So this is easy. We know that it is a Pythagorean triple, 5, 12, 13. Now we need to find the length of BD. Okay, so we have to get creative here. We know that CD is a radius and CA is a radius, so it has to be 5. So we do 13 minus 5, and we get BD was 8. So we had to use our knowledge of radii to help us get BD. Example 2, ABC is a circumscribed triangle. If the perimeter of ABC is 100, find AX. Now we're going to use that theorem that I called the ice cream cone theorem. The ice cream cone theorem says, if two tangents come from a common point, they are the same length. So those two are the same length, these two are the same length, and these two are the same length. X is not a midpoint, Z is not a midpoint, and Y is not a midpoint. That's another common mistake. Okay, so if this is 26 and this is 26, okay, we're doing good. If this one's 8 right here, then this one's 8 right here. And we're going to add all of those up. 26 times 2 plus 8 times 2. We're going to subtract it from 100. And then what? Divide it by 2, because these are equal segments, congruent segments, sorry, equal length. So AX is 16. Good problem? Doing okay? Okay, AC is a common tangent. AE is 10. BD is 3. BC is 12. Remember the theorem. When a radius meets a tangent line, you get a right angle. So when a radius meets a tangent line, you get a right angle. When a radius meets a tangent line, you get a right angle. Make sure you put those markings in the correct spot. Now let's just find every segment that we could find. What do you recommend doing here? We could do some Pythagorean theorem if you want to start with Pythagorean theorem. 3 squared plus 12 squared. You get 153. Then you have to factor tree 153. 3 root 17. So we know that one. How did we get that? We did a squared plus b squared equals c squared. And we took the square root of 153 and reduced that. So we have that part. To find the rest of the parts, it looks like we're going to have to use similar triangles and we're going to have to set up a proportion. So we could say 3 is to 10 as 12 is to, if I call this x, what would I say? 3 is to 10 as 12 is to, I would have to put x plus 12. You can't just put x. Good. Okay, 12 times 10 divided by 3 minus 12. You get 28 when you cross multiply and solve for that. So now we know that this one is 28. So that's AB. That would make AC 40. And now we could just say for ED, we could just do 12 is to 28 as 3 root 17 is to x, where this is x. I'm allowed to do that this time. I don't have to do pluses because those are corresponding parts. 12 is to 28 as 3 root 17 is to x. This is old stuff from the similarity unit. So 28 times 3 divided by 12, that would be 7 root 17. That's my birthday, 7/17.